our systems engineering. My name is Gavin Earhart, the team lead for this stage of the project, and here we have our engineering staff, the previous team leads and systems engineers for each of the previous design sections to allow people and students to take turns experiencing what that is like. Below, we have each of our drives, mixing and molding subsystem teams, with each of the team members below that. Next, we have our agenda. And due to our systems engineering design project being new to many of you, our team will give a brief project overview, an overview of our AGV, and a look into the design and interfaces of our subsystem teams from the perspectives of the drives, molding, and mixing. Then we will move into a live demonstration. Here, I'm going to pass it off to Eric, who's going to do a look into the objectives of the systems engineering course.
So the customer will come. Yeah,
no voice.
My voice is course today. Sorry.
So, just overviewing the systems engineering design process. We wanted to step into that a little bit. So, basically what happens is a customer, somebody will have a need, and they will come to an engineering firm or an engineer, and they want that need satisfied. And an engineer, a good engineer's job is to really dive into what is the need, what is the problem, what are all the aspects of this that we need to solve. And so they explore all of that, they explore the wider system that their design will operate in. And throughout this, you go through requirements definition, you go into the typical engineering design, mechanical, strength analysis, all of that good stuff. And you come to a product, which you then present back to the customer. Throughout this class, we basically follow this structure. I know this chart is kind of complex, so I'm going to step you through it real quick. So at the top left corner, there's that blue cloud, which is a complex problem solution. So oftentimes we have a problem and we might not even understand what that problem is fully. We just know we're not getting the best results with something, we need something, etc. So that person, the customer, will come to an engineer. And like I said, we explore the problem, we go through all the steps to do that. The first main step in systems engineering is requirements definition. So with that, you look at all the needs, and the customer and the engineer agree together to a document which has a list of requirements. And those tell the engineer what they need to design to, and they protect the engineer because the engineer can design to those requirements and the customer can't say, oh, you didn't do this, we wanted this. And they can say, well, we satisfied the requirements. So we've got the requirements definition. That would drop down to the red block titled SRR, which would be System Requirements Review. You would then step into conceptual design, where you would come up with an idea for a design. That gets presented at a critical review, a concept review, the next red block. You then drop down to number 3, which is preliminary design, where you work out more details. At the end of that, you've got most of the design done. It's not fully complete, but it's almost there. After that, you would go to the PDR block, which is preliminary design review. And then you step into detailed design where you finish everything up. You go into critical design review. And then if you jump over to the right side of the chart, you get into that taller block, number 5, where you actually manufacture, you fabricate your product, and you test it. So you're verifying that each component is doing what it's supposed to, that each subsystem is doing what it's supposed to, and then ultimately if the system is doing what it's supposed to. That moves up to block 6 at implementation, which is the spot we are today. We're putting our AGV in the plant, and we're going to see how it works. So now I'm going to step through the overall project. There's a lot of you here that haven't been with us all along the way. The engineers, this will just be a recap for you. Basically, what we did in this class is my classmates and myself were an engineering company, AGVX. And Dr. Fortney is the plant manager at a manufacturing company, and they make rotational molded plastic parts. And within his plant, he was having some production issues. So he wrote a letter to us outlining those issues, what was going on, and he asked us to solve the problem. So, as good engineers, we went through the problem process, like I outlined, and I'm gonna let each subsystem explain that as they come up. But to overview, we've got the plant here, and you all will see it more when you stand up, but I'm gonna show you on the screen. Basically what it is an open concept. So there's an aisle around, and there are 3 cells within the aisle. These can be placed in any orientation depending on the day's needs. So this is just one sample orientation, but they could be arranged any way. Those cells are the data cell, which houses the main computer. We've got the mixing cell and the molding cell. So I'm going to jump into the functions of these. So the plant makes rotational molded plastic parts. And to do that, they have 2 different types of powdered plastic. They come in these packets. And at the mixing cell, the current operation is that a plant operator will go to the cell and they will push a button on the computer there, and that will tell them the recipe for the plastic. So once they get that recipe, they have an access to the 2 different types of packets. They will load them into the loading area shown one by one. That moves into one of 2 staging areas, moves into the next staging area if it's empty, and then finally it gets sent to molding. At the molding cell, there are the 3 ovens where the plastic is actually cured. So like the floor plan, this is kind of fluid operation. These can be present or absent in any configuration given a certain day. And to talk about the issues a little bit more, they basically stem from an overburdened labor force. So at the molding cell, at the ovens, an operator would have had to have taken temperatures and taken those to the main computer. Someone would have to drop packets at mixing. And what's happening is at molding, an operator is either not taking a temperature as often as needed, or they're just not taking the data to the main computer. There's a regulation standard that says they need to record states of ovens every 15 minutes, which they're not doing. And then the other issue is the 20% downtime at mixing, where for whatever reason, operators are not getting packets there. This was all leading to unsatisfied management. Dr. Fortney was pretty livid when he came to us at first. He was yelling, throwing things. So basically, when we heard from Dr. Fortney, we wanted to get into the plant. We wanted to see what the problem was. So we came in, we chatted with him. We looked at each cell and saw how the operations were actually going, what was happening. We tried to look at the broad system in as many details as possible. Look who was involved, look what was involved, what we're going to have to deal with. We decided we were going to solve the problem with an automatic guided vehicle, an AGV, which is on the front of the table there, which would perform operations around the plant to solve those problems we were talking about. We determined that our AGV would need to perform some functions to solve this. So we, as a class of 9, we split up into 3 different subsystems. So each team had 3 members of their team, and we split up the functions that we defined into those 3 groups. So this tree here just kind of shows an overview of some of the functions that we needed to accomplish the solution. So drives would basically navigate around the plant. They would be in charge of moving the vehicle. Mixing would service the mixing cell, and molding would basically service the molding cell. We have chosen to use some basically miniature Lego computers, Lego NXT bricks. We used 2 of them on our design. Drives was going to be on one, and mixing and molding would be on the other one. Those use Bluetooth communication, as you'll see when we demonstrate. It works with the computers that are at each cell. So just to briefly go through our design process as a whole before the subsystems come up. We started in the requirements definition. So as we talked about several times now, we looked at the problem, we talked with the plant manager, they gave some requirements, we worked through building some more, structuring those in a way that we knew we could accomplish them, and then they told us what they actually needed. And we built a requirements list. And at the end, we got almost to 200 requirements. So that was quite a lot of work going into that. For sake of time, we didn't have a formal systems requirements review. We agreed over email. They looked at them, gave us comments, we made some changes. So then we moved into the concept design. We came up with a concept for solving the problem, which is shown. And we presented that to the engineers. So we walked through those requirements we had written, and they looked at them and said, how is your device going to do this? How's it going to do that? What does that really mean? And we talked through all of that. We got acceptance at that review, and we moved into the next phase of design, which was prototyping, trying out those design ideas we had. At this point, we broke down the system level requirements into subsystem requirements. So the system level requirements determined how we needed to solve the system level needs, which was the plan. The subsystem requirements we wrote determined how each subsystem needed to design so that we could properly go together and integrate. So as different teams working together, we could create one cohesive product. So we also skipped the preliminary design review due to time constraints as well. So we basically finalized the design, and we came to the engineers at critical design review, where we got provisional acceptance with a few comments from them on things we should change. So we moved into the last section, into the manufacturing and testing. We integrated all of our subsystems together, and now we have our product in front of you. So we're going to demo that at the end of today. Are there any questions overall before our subsystems? I was going to pass them to Nicholas anyway. So Nicholas is going to come up and explain the drive subsystem.
Thank you, Luke. And before I get started, unlike our AGV, the batteries for our display base did not last the entire time of this demonstration. So to prevent any issues, I'm going to go ahead and unplug them. As Luke said, my name is Nicholas Conner. I am the drives team lead for this semester for our project. I also have Gavin Earhart and Bethany Lear with me. Gavin introduced the presentation to us, and Bethany will be doing our portion of the demonstration. So I'll get into what we did as drives here. 4 drives, based off of those requirements that Luke talked about a few slides back. We came up with a goal, and that goal was the drives to provide a method for safely maneuvering around the plant to allow the other subsystems to perform the required tasks. And this is how we went about doing it. So starting out with our concept, we didn't really know what everything would entail from this, but we knew kind of an outline of what needed to be done. So we started with a few very rudimentary ideas to get us started. And I'll step through these pictures and also what goes along with those. So we knew that there were some height requirements for all the different subsystems. So we wanted to be able to get all of our components as low to the ground and with as little crossover between subsystems for them to be able to have the most room to work with. We also wanted to have centralized driving wheels. We wanted to have full movement in both directions. Those guided completely, so no stray robots at any point. And we also wanted to have maximum stability that we could, to not have any issues with it tipping over. So the first picture on the top left, that shows where we started with our interfacing. So to get that layered concept, we had to come up with something to start with. And what we came up with was we went to the whiteboard back over here, started drawing stuff out and said, all right, I think I can work with this portion. The next group has this portion, the last group has that portion. And as you'll see, that didn't quite end up being what the final product was, but that's what we used to start getting our design together. The bottom picture was what we first started doing for our first prototype, seeing if our concepts would work with the centralized drive wheels and having the guided movement in both directions. So we put a few things together, started testing it, saw that that worked, so we moved forward with what we were doing. What we did not realize at the first design of that part, which quickly came forth when we were testing it, is on the front and the back. Can't see it on the back, but there's only one of those wheels located there. So if something hit the front corners, it was very easy for it to tip over, which did not meet our design goal of having maximum stability. So going forth, I'll show how we fixed that as well. For our design development, like I said, we had the centralized pivot wheels. For that, we had 2 light arrays. The light arrays are what we use to follow the lines you can see around the plane here. So we have those located both on the front and the back. And having those centralized pivot wheels really helps simplify the movement, switching between those 2 directions. We also wanted to have that for the maximum use of the AGV. Instead of having everybody stuck in one spot and only using one side of the robot, we were able to use both the front and the back with that. Like I said, with the layered base design, we wanted to provide the most height for the other subsystems. We also have a flat top for ours. We wanted to do that to simplify the physical interfacing between the different groups. And like I had said, with putting the wheels around, as you can see here, we do have the wheels on the sides. And in the next slide, I'll show that placement that fixed the stability issues. But we were trying to get all that weight as low down to the ground as we could to help with stability. So having all of our components within that little section really helped with lowering the center of gravity of the entire AG. For our concept design, we met most of the goals that we had, I think actually all of them. We had the centralized pivot wheels, so the gray wheels located in the center of the AGV. Those were powered by the motors. We were able to fix our stability issues with putting wheels in all 4 corners of the AGV instead of having them located in the center on the front and the back. We still had our layered concept that we had originally started with, and we had the guided movement in both directions. So it's a little bit hard to see it, but under some of the components on the front and the back, that's where the light arrays were placed for us to have that movement that we were trying to reach. Moving into critical design review. So with this, we had more of our design finished. We were trying to have everything finalized to show that everything would work properly. So one of the things that we realized when we were doing our testing, and it came forth really in our concept review, was that our object detection. So with our device, we have means to see if there's an object in the way so we don't run over people or things. And with that, we had sight for our primary object detection. And then as a backup for our secondary object detection, we had a bumper, which had a touch sensor. So if anything got past the sight sensors, it would trigger the bumper and would stop the AGV. So for our primary object detection, we had one sensor, which is the red block located at the front, which is the left side of the AGV. And that wasn't covering the full width of the AGV. So we needed to add something else into that to be able to fulfill our needs of detecting any objects. So we ended up placing the sensor located on the top of the AGV. That combined with the previous sensor gave us the full width coverage of our AGV. We also had all of our components mounted. As you can see in some of the spots, there are little gray pieces scattered around. Those were used to secure all of our components. All of the components that we used were either Lego or Lego compatible robot pieces. So we were able to use Lego connectors to really make sure everything stayed in place. We have an emergency stop button as well, that we previously had a rod to make it so you can trigger that emergency stop from the outside. So as you see in this area right here, you can see the rod right there. Right there and there. So previously we had just the rod on the bump or on the sensor. So it could be pressed as the sensor is located in the center and you don't have to climb into the robot. At our concept review, it was pointed out that that might be a safety hazard for any of the users in the plant. So we added a cap to the end of that to prevent any injuries that might arise with not having anything covering the end of that rod. We also added bearings and shafts to all of our wheels to help reduce friction and make everything go a little bit smoother. So from there, we had everything manufactured. And for our manufacturing processes, we had 3 different parts really that we made. And I'll go back a slide to point them out a little bit better. The bottom layer here and the vertical components, that's what we refer to as our base. The piece on top where everybody would integrate with us, that was our top plate. And then the bumper is located on the left side of that image. So for those parts, the base and the top plate, both of them were 3D printed. We did that based on the complexity of the components. That was the easiest way for us to manufacture them. And then for the bumper, we cut that on the laser engraver out of acrylic. So all those components were made here. Throughout the course of the semester, there were a few things that we learned that we wanted to highlight here at our presentation. The first one is communication between teams and within teams is very important. Also documenting all those things that you communicate. One of the biggest things that we had to work with us, to help us with all this, was our interface control document, or ICD, showing where everything would fit together. And so you have accountability. That way you can tell somebody, hey, this is what the document says, that's what you have to work with. Otherwise, you're gonna have to be making a lot of changes to make everything work. The next one is don't be afraid to update or change something if it's not accomplishing what it needs to. So there were times where we had something, great idea, started making it, and it just didn't work like we thought it would. So we'd have to go back, make those changes. And sometimes that involved other groups having to make changes as well. And you really don't want to have to make other people make those changes as well, but you have to do what you have to do to make things work. So that was another thing that we found very useful to learn throughout this. Another thing is testing ideas early to see what works, understanding what works, and figure out what doesn't work. So that robot that I had showed at the very beginning that had only one wheel in the front and the back, that's something we did in the first couple of weeks of the class. So we were able to start figuring out what worked. We found that having those central guiding wheels did work, but we had stability issues. So we did some more testing, redesigning, and got things to work how we wanted to. And lastly, if you don't know something, admit it and move on. So it's very easy when you're presenting information. You think you know everything, so you start to, in a sense, get into an argument. You don't want to be proven wrong, but at the same time, you don't know the information. So it's much better just to upfront say, I don't know that, I'll have to get back to you on that, rather than dig yourself into a hole because you're just going to get in more trouble. On the flip side of that, taking the hit. If there's something that you do know that might be wrong or is wrong, and you just didn't have time to fix it, or there was some other reason why you weren't able to fix something, admitting it, taking the feedback, the critique, and then moving on with everything. Because in the end, it's not that big of a deal. It's not going to be the end of everything. So you just gotta roll with it. And that one was probably the biggest one for me. We had some dimensioning in our concept review. They had too many digits on it, so too precise of a number. It was unrealistic. That was pointed out to us. We got to critical design review, and we did the same thing. And it got pointed out again. It was my fault. So I admitted it, said, I know that's wrong. We didn't find it until it was too late. So I just took the critique and moved on from there. So that wraps up what Drives did for this project, creating our AGV. And now I'll be passing it off to Savannah for mixing.
Hello, everyone. I'm Savannah Tabor. I'm from the mixing subsystem. Also on my team, we had the team lead, which is Matt. And then we have Luke as well on our team. So basically, I'm just going to run through all of our steps of design and how we really took into consideration of all the aspects of systems engineering. We also have a notebook here just in case y'all want to look at some of those documentations. So we have like our ITD, as Nick was discussing, to define everything within the subsystem teams. And we have our system level and subsystem requirements in there, a project summary. Overall, for the mixing subsystem, we were like our goal defined by our requirements was to receive packet recipes, store that, and also deliver the packets into the mixing cell. And the whole purpose of us being contracted by Mix It Up was to ensure that the mixing cell never ran out of packets. So just some initial brainstorming. We were given a bunch of stuff, basically boxes of Lego materials. So we had like Lego motors, building blocks, little pegs. We even had like maybe 6 or 8 different servo motors as well. So we were like, okay, well, we can use this servo motor to help us like dispense our packets into the mixing cell through like a slide mechanism. But with that, we were like, well, then we were posed with the issue of this feature here. Well, like, are all the packets going to slide out at the same time? So we developed our design more by using a conveyor belt system. And with the conveyor belt, it allowed us to just have that horizontal platform for our packets to sit on. And so we could store a bunch of them and also deliver it easily. With that, we were able to prototype with the parts we had. So the image that you see come first on your left is all the Lego components. Nothing was custom there. We even hooked up the Lego motor to run that conveyor belt, and we were just tweaking some things, seeing what the response was. Then we got into trying to make our design more custom, and we were able to 3D print a conveyor belt, actually from our 3D printer in the lab, out of a flexible TPU material. We were able to 3D print wheels as well to drive the conveyor belts and just make a more custom design to what we needed and incorporate as many packets onto that conveyor belt. Basically, to get as much packets on there and deliver them without needing to be refilled so quickly by the employees. And the last image that you see on your right is a more solidified prototype with the 2 Lego motors themselves driving the conveyor belt. At concept design review, we presented this idea to the engineers and we were given some feedback on it, but essentially, like I said, it's 2 Lego motors driving 2 conveyor belt systems. One will hold the yellow packets, and one will hold the black packets. They will then funnel down into our packet chute and drop into the mixing cell. So from there, we were permitted to go on to the critical design. And this is our bottom layer. As you can see, there was changes made. First of all, the structure is more well-defined, and we took into consideration of how we were going to attach to the AGV itself. So we used some Lego pins that you can see as the call out 8. And we redesigned our packet chute as well, just to prevent any packets from being jammed whenever they fall off the conveyor belt system into that chute, so that it can freely drop without any jamming. And building on top of that bottom layer of our design, we have our top layer. Mixing subsystem took the responsibility to hold and attach the Lego NXT bricks and also some equipment used by Drive, such as a battery pack and what we call smugs. Basically, you can just hook up more sensors to that block. And we also finished defining how we were going to stabilize our packets on the conveyor belt system. So whenever the AGV is going around the plant, nothing shakes it and makes those packets tip over, and then that causes jamming. And then also the packet stability feature allows the packets to stay in place whenever the conveyor belt itself is printed. So moving on, today you will see our manufactured product. And we obtained a lot of learning curves from this course in general. So thank you, Dr. Courtney, for giving us all your wisdom. Basically, everyone has something to bring to the table. Everybody has their strengths and weaknesses. I know for us, or for my team, we were all really diverse and had a variety of strengths, such as Matt is really great with coding and was able to put code in the Lego NXT brick like quickly for us to just simulate something. And then Luke was eager to help in any aspect, always willing to do anything crazy for the design. And then for me, organization was a big piece, documentation, recording everything. So we really gained a big respect for systems engineering throughout this whole course. So just by documentation and then having to design on top of that as well. And communication is key within your subsystem teams. So like every day we're texting back, like, hey, this and this, or if I see you around, I'm like, hey, we need to work out this. So, and with them, they made work or school not feel like school. So it was easy to really enjoy this project and learn great detail. Any questions for mixing? I'm gonna pass it to Andrew to go over molding.
Hello, my name is Andrew. I'm on the molding subsystem. I'm basically going to walk you through the same steps that Drives and Mixing just did, going through, or not through our requirements, but straight into how we got to our conceptual design, and then how we moved on and progressively got more and more detailed. So starting off with our goal, what we defined is that we needed to detect, measure, and record the state of each of these 3 ovens that Luke mentioned earlier, and then transfer all of that data onto the main computer. So starting with brainstorming, like the other groups, when Dr. Ford introduced this project to us, he said that no one had really used servos to accomplish this before because it's kind of an awkward thing to do. So what we heard was we're definitely going to try to use servos to accomplish that. So we knew right away that these little servo motors, they rotate. So we needed to figure out how to turn rotational motion into something that's linear. So here are some drawings of where we were just experimenting with different ways to do that. And then once we settled on a rack and pinion, we kind of started messing around with how can we make that rack and pinion actually accomplish that. So we're going to be out in front of these ovens. How can we get a temperature sensor out and into those holes so we can actually take the temperatures? So we started messing around with this rack and pinion driven by what was originally a rubber band, actually, which did not work very well. So we knew we could rotate out to them, and then we knew we could rotate also into them, basically. That's where our brainstorming led us. And so we started to try to build this with some of the Legos that they mentioned earlier. So on the left is a very crude early construction of this, where we have these gears that are driving something from a rotational motion out and actually making it move forward. And then I think one night, Will went crazy and actually built the entire thing out of Legos. No idea how long that took, but we brought this early prototype, definitely helped us a lot. It really validated that this concept could really work, that we could rotate and extend linearly using the same exact form of motion. So following this early design development, we were able to reach this for concept review, where we decided we needed a temperature sensor, something to actually see which of these 3 ovens are here at any given time, and then 2 servos in order to accomplish each of those types of motion that we needed. So moving on from concept, right about this time, as you can see, the arm up top with the sensors on it, it's very crudely just sitting up there on the pole at the moment. So at this point in time, we had no idea how that stuff would actually sit up there and just be there. So we needed to basically go back to the drawing board following concept design and just actually create something that could hold like all of these different sensors in this compound rack and pinion gear we had come up with, because without something to hold it, it's not going to do its job. So we came up with this basically sandwich of acrylic plates that could hold each of these different components up there. And after a little bit of tweaking, I think we built this thing 3 or 4 times. Eventually we got it to where it was consistent, it did what it needed to do, and that is how we got to our critical design, which everything here is going to be laser cut from acrylic. We actually decided to leave the presentation. Did you do that, Dr. Corey, or did I do that?
I did not. Sorry. But while you're transitioning, I will ask you, did you ever have any idea how useful all those kinds of doodling and practicing drawing would be? I love those illustrations.
Yeah, when we first started, I mean, like Nick showed it on the whiteboard, it's hard to go from absolutely no idea of what you want to do to something so detailed. It's got to complete 200 requirements. So when we started, I was like we had 3 sections of team leads, and I was the first one. So I basically went around to each group and just was like, tell me your ideas, and I was just trying to draw them. And I think once you can see it, you can really start to like build onto it and like adjust from there. So yeah, that was like very helpful for me, I know, because I didn't know where to start.
Yeah, just even in your presentation, I was just thinking that ability to illustrate like you have is really helpful.
Yeah, so moving on from a drawing to where we ended up with critical design, where we had just limitless changes. I mean, and with something like this, where we changed towards the end, if we had to make a change, it changed 25 other things. So we had to completely rebuild it anytime something small is off, which took a lot of time. But basically, this is where we ended up for critical design. And this was our manufactured product towards the end, as you can see up here, and will be demonstrated for you shortly. But some of our learning curves is that other subsystems are going to have tolerances that we have to account for, which basically means, so the little holes inside these ovens are, I mean, thousandths of an inch gap that we have to try to hit. So we designed our section very precise so that it could get and actually take that temperature. What we didn't take into account for was that we're sitting on top of another team, which, I mean, we told them what height to be at, but we didn't tell them how tight to be at that height. So like, we ran into a problem where we set it on there and it's basically like almost there, which does not satisfy a requirement ever. So that was definitely a learning curve, which got fixed with 2 small pieces of wood. But yeah, definitely another communication thing, I guess, just understanding what affects your side of design. And also be willing to change a part that's not performing as well as required. You're very reluctant to stay with something that you think is gonna work the entire time, and you realize it's not. So the earlier you change something in a process like this, it's like, it'll save you hundreds of hours, honestly. But yeah, those are the biggest takeaways that we got, going through this semester. But yeah, like they were saying earlier, thank all of you guys, and thank you, Dr. Courtney, for all the feedback this semester. And now we're gonna do our live demonstration. Luke, or sorry, Matt, Will, and Bethany.
So there's room around the table. We're gonna let the engineers get their spots so they can see the best. But if you want to stand and get closer, you're welcome to do that. We're also putting it up on the screens.
Yeah. Okay. I'll have you show this.
So I'm just turning all bricks on, starting the code, making sure that everything that has a battery is turned on.
A live demo, no smoke and mirrors, huh?
Smoke and mirrors.
Maybe some smoke later.
Ready?
I think so. So real quick, before we start it, we're just gonna really quickly describe, what the process is gonna do. Anyway. Is it this
No,
one?
you're good.
Is it this one?
Mhm.
Okay. Hi, I'm Bethany Lear. I'm on the drives team. With me is Luke on mixing and Will on holding team. Really quickly, I'm going to describe kind of what the process that it'll do as it goes around the plant will be. So we're going to just run some regular operations of the AGV first. So it'll drive around. First, it'll hit this mixing cell, and Luke will describe kind of what happens there when we get there. Then we'll hit the molding cell, and Will describe what happens when we get there. The first drive around, we're going to go ahead and let it roll over some different lines. Breaks in the line. So we have a 2-inch line, so it will drive over this one and continue moving normally. On the 3-inch line, it will stop motion because that was our requirement, was to stop at a 3-inch line. It will signal that it's lost and send a page. Then we'll drive around again and we'll do some object detection, making sure that it sees the objects and such as we drive around. I'm going to use this because it seems to be the best object that we have that will not get tipped over accidentally. If we do have the e-stop, you can see it's this little red button. I don't know if it shows in there. It probably won't because of the camera, but there's a little red button on the side. That's our e-stop. We're kind of opening it up to you guys. If you want to just say, when you press the e-stop, we'll go ahead and press it just so that it's tested. The only time it will not work is within the restricted zones when it's following the line in, because that was part of the requirements. It's like it's a restricted zone. We don't need to have stop in there. Any questions before we go ahead and start? All right, I think.
One more caveat.
Oh yeah, go for it.
So if it's in a cell, servicing a cell, there are moving pieces on the vehicle. If you press the e-stop, it will stop before it conducts the next movement. But if it's in the middle of a movement, it will continue to move. It's not a really stop. It's like over.
All right, well, we're all good to go. We'll go ahead and start. And one note is that in the code, which I do have open on the computer, if anybody wanted to look at it, we do have the settings to play sound when it does move, because that was part of our requirements. But shortly before we presented our brick speaker blue. So it's not going to make the sound that it's supposed to, but it is there and it was working in the past. Unfortunately, it will not be making the sound as it's supposed to.
Those sounds are so annoying. I'm gonna miss
Oh, it was
them.
a horrible noise, but it was working. Oh, okay, I guess it's lying to me. That's okay. We'll see what happens. You go ahead and do 2 incline over on this side. So continue driving over the 2 incline. It is working. It's just very faint.
So now it's gonna pull into mixing, and like we talked about, it's gotta communicate with the computer at the mixing cell. So it's going to talk to that computer, the computer is going to give it the recipe for the number of packets. So we've got the yellow packets here and the black packets here. And once it communicates, let's give it 1 and 1.
1
1 and 1. So after it talks, it'll take a few seconds, and then you'll see 1 yellow packet and 1 black packet drop.
All right, it's coming in now.
I'm gonna try to operate this without crashing.
So 1. Sending it back right now.
Now we wait.
You stop this press. Okay, so that's a thing. There's good message.
That's not our plant, by the way, that was Dr. Ford. So, thank you, Luke. You're welcome. Anytime. That's batch 1 of 1. So we moved that into the staging area and then the next staging area. So then we can drop another batch, which,
How many would you like?
yeah, does anyone have a number they would like to throw out there?
2 and 3.
2 and 3.
2. 3. All right, sending those takes a minute.
I'm not a certified plant operator. Showing great potential. Excellent. So we've got 2 yellow packets and 3 black packets. So now it's done servicing. It checks how many packets it has to know if it needs to be refilled, and then it goes out. It detected that it still had enough packets to service it next time, so to speak.
I'm gonna go ahead and do the 3-inch break in the line over here on this side, and it should stop all motion once it detects there is no line. Yep. So now it should send a page that it is lost. It takes a second. Alright, and makes a noise. So now we move this.
Said it's lost.
Yep. And then we center it back on the line. And go ahead and say you're good to go.
Okay, so now it's coming up to the moment. So, and to be completely transparent, a Lego temperature sensor will not read the actual temperature, unfortunately. So that's very disappointing. But what's going to happen is it's going to turn this little Wally eye that it has up here, and it's going to see which ovens are present. So right now, all 3 are present. So it's going to come back in, and it's going to turn 1 at a time to the ovens, and it's going to put this thermometer into that oven at least ½ an inch. And it's going to wait there 7 seconds. We could have made you wait the whole 60, but I thought that'd be pretty terrible with no reward at the end to get the right temperature. So it's going to do that for each time, each one. And we're going to go around the plant one more time, and we'll open it up for you guys to pick and choose which ovens are there. So you can see that it does differentiate whether an oven's there or not. There it is. Very nice. So now it's going to navigate out, and it's going to continue driving until it reaches this nice wooden panel that we have up here that's representing main computer, where it takes all the information from the packets it delivered and the temperatures that it did not take. Tells the computer what's happening in the factory, and gives it the data.
And then once it sends that data to the computer, once the computer says, I got your data, thank you for that, it will display a 30-second screen on the drive's brick, which is on the left side for me. And it'll be 30 seconds to give you the opportunity to say it's the end of day or not. If it's not, it will just continue going after that amount of time.
So right now, it's giving me one transmission at a time, not temperatures, packets for recipe 1, packets for recipe 2.
Not temperatures, that has a ring to it.
Sample 1, and 2 and 3.
So what's the problem with temperature?
I mean,
It's the actual sensor.
It's just, is it getting a temperature, but not a bad one, or?
so it's taking too long to come up with the temp, but the little half an inch that it can get in.
Is it the response time?
Or is it? Put it all the way in, you could probably get it.
Are you gonna do an object?
I'm gonna do it once it gets past next time.
Okay, so approaching mixing again. It will request more packets, which an operator will bring if it gets to less than 2 packets. So let's see, how many do we have? We have 5 yellow and 4 black. So let's do 4 and 4. Sure.
Go away requests. Yeah, sorry, this takes a little while. All right, here we go. 4 and 4. Notice the little bloop sound that it makes when it drops the packets.
There you go.
That was operator error there. Lou.
There I go again. Come on.
Uh-oh. Did it move and one not come out?
We misfired once.
Hmm.
I'm not really sure what happened to him. The next one's ready to go. Interesting. Okay, so now we're down to 1 packet on each side.
Now it says load packets.
So then we just come in and there's a door on each side. And we can just load the packets in.
And while they're loading the packets, and a much more lighthearted note, we changed our object detection for the ovens to this sensor that really makes it look like Wally's driving around in the factory. It's much more enjoyable.
I don't recall anyone mentioning how it's determining where they're stationed or how it determines.
So those little Wally eyes are an ultrasonic sensor. It sends out ultrasonic sound waves and it receives it back. It says, nice
No,
little.
I'm talking about like if you're driving around.
Oh, okay.
The
Right.
colors-
yeah.
So I don't know if you can see it very well. You can kind of see this color sensor here on the ground. So there's a different color for each station. So the green is going to be mixing, molding is red, and the data is yellow. So when the color sensor drives over that, it will see the color, and depending on which color it is, it will determine which direction it will pull into the cell. And then it also determines which function it'll call, like it'll say we're at whichever station, and that determines what brick 2 will then do once we get in there. Oh, I didn't hit go. That's not it.
Okay, there we go. So that's one other thing that had to happen after packets are loaded. You have to physically press a button to let it know that loading's complete so it can continue moving and doing what it's supposed to do. All right, do we have a number we'd like to send?
With a limit.
2 and 2.
It's supposed to be
Two.
2. 2.
We just wanted to make it.
Let's do 5 and 5.
Good with
I wanna
that.
see Luke push that thing some more.
Oh, man.
Oh, and while he's doing that, which ovens would we like to have present?
Remove the center one.
The center one? Should I turn it off first?
What is it, 5 and 5? Hey, 4 came out that time. And 5.
Like a vending machine that just doesn't give you the skills you want to buy. Take the game, that one time.
Uh-oh.
Nope, you get it. It's in there.
Is anybody having flashbacks to Lucy and the candy? So we got 5 and 5.
Oh, yeah. And we'll go ahead and do an object detection over here. That, is this an okay spot to do it? All right, and it did stop, and there is space, let's see, can you
Well,
see
like,
it?
see it if,
I was
I
gonna
don't
say, if
think you
anybody
can.
walks over here, it was detected by the primary object detection, it did not contact. And I left it there, and it's definitely almost been 15 seconds, so the 6 seconds, it would have made a noise, and then at another 15 seconds after that, it'll send a page, and it'll say, hey, move whatever's in my way. Did it send that?
just got it.
Yep.
Sure you did.
And now I will move this, and now it will send another page that says the object has been moved, and it'll go after about 2 seconds. There's pauses for like Bluetooth and stuff. Try to use my hand one time, my hand's too small. Yeah. One, but it does not like to roll over the dowel rod.
Just
So
don't test
you
it.
can go get it. So the issues that we found is that for the length of the time that we were now given, the time is different. So the 2-inch line, and with our center drive wheels, when it pops up over. When it pops over, it does not register. It thinks it's lost because the line moves itself.
Yeah. Change that.
Of course you don't know, Lee, but it's a live demo.
That's it. You know what happened? It's gonna send everybody.
So the distance sensor got stuck on the wire.
So it's looking at the first one the whole time.
Yeah, thanks everything's good.
It's slipping gears. You guys like to see it again if we fix the wires?
That's okay. Okay. I trust you.
All right. It's kind of common.
Yeah, it's just the center wheel motion.
So what happens with that, the front and rear wheels are the omnidirectional wheels, they allow to move in 2 directions freely.
If I was standing in the way.
When those tires or those wheels hit the dowel rod, it pops up onto it slightly, but doesn't quite go over because it's weight distribution. We didn't have an accurate weight distribution when we were testing, so we didn't see this issue. But what happens is when those front wheels hit the dowel rod, it picks up the whole AGV from that front end a little bit and takes enough pressure off our drive wheels where they don't have enough traction to keep pushing over.
So when did you recognize that problem?
That was after critical design review.
After integration, right?
Yes, yeah, once we had put everything on and we had the weight distribution like it is right now. We had done a test with more weight than what we were anticipating the entire AGV to be sitting on the center, so all that weight was over those drive wheels, and it didn't have the issue popping up over the dowel rod with those hard wheels.
So I'm gonna.
You wanna let it go?
Yeah, so I'm gonna let it go one more time around, and we're gonna cover up the color sensor as it goes, all the color spots as it goes through, so you can see after it goes around a certain distance, it will stop and will not continue driving. So we use the swim fine brake to continue driving, but will not see the color.
Oh, that was quick.
So it went around one time around the plant without seeing anything, so then it stops and it should say that it did not find any,
Still waiting.
Yeah.
Okay, something's coming in. No cell phone.
so then it's telling us to check the color sensor to make sure that everything's proper or that everything's on board.
And do the e-stop.
E-stop, that's right, we can do that, so we can just restart it.
It's amazing.
Start it back with regular. And across. And then I fixed it back on the line and go. Wait a couple seconds and then I'll continue driving after that. And then we'll just continue as well. Anything else that we wanted to see while we were going around?
Well, other folks come up there and see it up close.
Yeah.
3-page detail design.
Anybody else wants to come up a little closer while we're mixing?
Why don't you guys stop it for now? We'll wrap things up and then you can run it again and let whoever wants to get up there close.
Put it back in data. Start.